I am now calling Professor Vilmos Totik to give his lecture entitled Erdős on polynomials. Please.
Thank you very much. So my task will be to talk about the work of Paul Erdős on polynomials. Already Erdős mentioned that Erdős had many results on polynomials, and they are in different subjects. He wrote most papers on interpolation. He had some results on discrepancy for zeros, for inequalities, growth, some problems on lemniscates, more papers on orthogonal polynomials, but somehow always interpolation was in the background, and spacing of zeros, and finally geometry of zeros of derivatives. He wrote many of these papers with his lifelong friend on Paul Turán, and there are also some very relevant papers with polynomials and integer coefficients, though they are also related with number theory. Now, in the last Erdős conference from 1999, in the proceedings, there are actually two extensive surveys on interpolation. Lubinsky and Vértesi wrote. On inequalities, Tamás Erdős wrote some surveys. On lemniscates, what happened was discussed by Yeremenko and Heyman and Borwein. And also polynomials with integer coefficients were discussed in two papers by Borwein and Erdős. So I will talk about the rest. Discrepancies, orthogonal polynomials, spacing of zeros, and geometry of zeros of derivatives. Growth, this is not working. Oh, this fourth topic, growth of polynomials, will not be discussed, and there hasn't been a survey to my knowledge. But not much happened in that field. The conjectures of Erdős, there are still conjectures. So let me start with Chebyshev polynomials. The Russian mathematician Chebyshev was working on some problems in mechanics, and he came across the problem how to replace x to the 4 by linear combinations of smaller powers. That is, he needed an approximation to x to the 4 of x to the 4 by smaller by combination of smaller powers, and he actually solved the general problem that where you can approximate x to the n on -1 by linear combinations of smaller powers. And if we called Tn the error of approximation, which is the infimum of the norm of polynomials, where the leading coefficient is 1, x to the n. You know, if you subtract from x to the n a linear combination of smaller powers, you get a polynomial with leading coefficient 1, basically. And you want to minimize the norm. And in this talk, the norm will be always supremum norm. So the norm of Pn on any set is just the supremum of the absolute values of the function. And Chebyshev showed that this approximation problem, the solution is 2 over 2 to the n, and the extremal polynomial is what I wrote here. A constant times cosine n times arcus cosine x. So this is a polynomial, even though it doesn't look like. So that's an explicit solution, and this problem basically started approximation theory. The solution of this problem. If you look at the zeros of Chebyshev polynomials, these are these red dots here, and you project them up on the unit circle, then you get points on the unit circle that are equally spaced, so they are uniformly distributed. And what Turán and Erdős observed was that if the norm is not much larger than 1 over 2 to the n, not much larger than the optimal norm, then the same phenomenon happens. If you project the zeros up on the unit circle, then the distribution will be almost uniform. So this is what I call the first discrepancy theorem of Erdős and Turán. So look at a monic polynomial and assume that all of its zeros are in -1, 1. Let this be xj. And assume that the norm of Pn on -1, 1 is not optimal. You know, the norm is not minimal, but at most a constant times the minimal norm. And what they proved that in this case you can get a bound. I mean, you can estimate how many zeros are in a given interval. So you take a subinterval of -1, 1. This is the number. On the left is the number of zeros in that subinterval. And you subtract this expression, and the error is that much. This is a discrepancy term, you know. It tells you basically how many zeros are in a given interval. And first I would like to speak about what happens if you look at the polynomials not on -1, 1, but on, say, on 2 intervals or several intervals or on a curve. So what happens? We have to understand what is this 1 over 2 to the n and what is this distribution, this arc sign distribution in those cases. So I will have to speak a little bit about elements of potential theory. First, equilibrium measures. Take a compact subset of the plane and put a unit Borel measure on that set and look at this so-called logarithmic energy. It's just the double integral with this logarithmic kernel, double integral of this mu. Now, if there are cases when this is always infinite, like if E is a one-point set, but if this is finite for some measure, then there is a unique minimizing measure, mu E, which is called the equilibrium measure of E. You should think of E as a conductor, and you put a unit charge on this conductor. The charge can move freely in the conductor. And when it doesn't move, so it's in equilibrium, then that's exactly, the distribution will be exactly this equilibrium distribution. For example, for -1, 1, the equilibrium distribution is this, which I call Chebyshev distribution. From now on, this will be called Chebyshev distribution. If C1 is the unit circle, then, or you consider unit disk, then the equilibrium distribution is just the normalized arc measure. So it's just the uniform distribution on the boundary. We need the concept of logarithmic capacity. You look at the minimal energy that we just discussed, and with this minimal energy, the capacity is just e to minus ik. For example, if you have a k is a disk of radius or circle of radius r, then the capacity is r. And the capacity of an interval is 1 over 4 times the length. So the capacity of -1, 1 is 1 over 2. And that's exactly why you know, in Chebyshev problem, there was a 1 over 2 to the n. In general, if you have a, I'm sorry, if you have a polynomial with leading coefficient 1 here, then the norm of that polynomial on that set K is always at least as large as the nth power of the capacity of K. So this is a theoretical lower bound for this norm. Now there are two related quantities. The transfinite diameter associated with K is obtained by, you look at K, you put K, you consider K point, n points on K, you choose n points, and you want to choose them so that they are as far as possible, so they are spread out. And you measure, how far they are spread out by this product. You look at the mutual distances and you take all the products. And when you normalize them, there are n times n minus 1 factors in this product, then it turns out that this quantity has a limit, delta K, which is called the transfinite diameter of K. And what we have already discussed is the third quantity, the Chebyshev number. So again, you look at the infimum of all the norms of monic polynomials of degree n on K. In this case, when you normalize, you take the nth power, then the nth power tends to some number, which is called the Chebyshev constant associated with K. And then it's a theorem of Fekete, Zygmunt, and Szegő that these three quantities are the same. The capacity, logarithmic capacity, the transfinite diameter, and Chebyshev constants are the same. Today we use mostly capacity, and of course Erdős knew this, that they are the same, but in all his life he was referring to transfinite diameter. It was invented by Fekete, or Fekete introduced transfinite diameter, and of course Erdős knew Fekete very well. So let's go back to the Erdős-Turán discrepancy theorem. So we have monic polynomials with a bound on them, on -1, 1, and you can rewrite the discrepancy theorem that arc sign distribution is just this integral from A to B, what is here, and you recall this is the Chebyshev distribution. So if I also introduce the normalized zero distribution, so you put a unit mass to every zero and divide by n. There are n zeros, so this is a unit measure. And so again, this Chebyshev distribution is just the equilibrium distribution. I already mentioned this. So in this reformulation, this form, the Erdős-Turán theorem is just that the normalized zero distribution differs from the equilibrium distribution on any subinterval by at most as much as what is on the right-hand side. Now this is sharp, this is exact. They already knew that you cannot do better than that. So this is a correct estimate. And this already tells us what one should do in general. In general, you should look at how much the norm of Pn is above the theoretical lower bound, which is the nth power of the capacity. You should compare it, and then the zero distribution should be somehow close to the equilibrium distribution. So let me formulate the general discrepancy theorem. Let K be a finite union of smooth Jordan arcs. It's important that I'm talking about arcs. So homeomorphic images of the unit circle, things are different when there are Jordan curves. So, like images of the unit circle. This is unit images, arcs are images of the unit of an interval. Yeah, probably So Jordan arcs, we have finite union, and we will discuss subarcs. So J is a subarc, and we will need neighborhoods of subarcs. So if J is a subarc, J star is something like what is on the picture. And recall again that the norm of Pn is always at least as large as the n power of the capacity. Again. And now, so I will look at how that is the norm, how far is it from the theoretical law, from the n power of the capacity. An is this constant. And again, un is the normalized zero distribution. And after many, many different works, the strongest result is this, that if you, An is defined this way, and you look at any subarc of K, then, and you look at how many zeros are there, and you subtract the equilibrium measure of that arc, is the same as mu K R. Mu k j, then the error is at most as large as log a n over n under the square root sign, exactly the same as in the original Erdös-Turán theorem. In particular, if the nth power of the nth root of the norm tends to the capacity, it means that when you take nth root here that An is not exponentially large. An is sub-exponential. So if Pn is, the polynomials are not exponentially larger than the n power of the capacity, then the zeros, the asymptotic distribution of the zeros is just the equilibrium distribution. Now, this is not true anymore, what I just said, for Jordan curves, so which are like distorted circles. Just imagine z to the n on the unit circle. In that case, z to the n is minimizing the norm, which is 1. The capacity of the unit circle is 1. So we are, z to the n is a minimizing polynomial. And all its zeros are sitting at the origin, while the equilibrium measure is on the boundary. So you know, in that formulation that I had before, one really needs Jordan arcs. So what happens on Jordan curves? First, I go back to two old theorems. The first is a theorem from Jentzsch from 1918, which says if the radius of convergence of a power series is 1, and you look at the zeros of the partial sums, you take all partial sums, all zeros, then these zeros are dense at the unit circle. So around every point of the unit circle, there are infinitely many zeros. And this was sharpened by Szegő in 1992. Szegő says that if the same situation, if you write for the zeros the polar form, then that is e to the theta j and are the arguments of the zeros, then Szegő's theorem says that there is a subsequence such that this theta jn is uniformly distributed. These are asymptotically uniformly distributed. And also at the same time, the radii of the absolute values of the zeros are about 1. So this is really sharper than Jentzsch theorem. So Szegő's theorem says an asymptotic uniform distribution of the arguments of the zeros. Now, Erdős and Turán had a second discrepancy theorem, which I formulate now. So, C1 is the unit circle, and again, we look at a polynomial, and we write the polar form for the zeros. And the second theorem says that if you just look at the distribution of the arguments, then how far it is from the uniform distribution. And the error is given on the right side. You take the norm of Pn, divide by the square root of the product of the first and last coefficients. take the log, divide by n, take the square root. Now it's clear that the norm of Pn on the unit circle, when you take z is absolute value 1, the norm is less than the sum of the absolute value of the coefficients. So immediately we get this is not working anymore. I can use this. All right? Yeah. No, I think that nothing is working now. Oh, okay. Okay, we may have. Nothing. It would be difficult to continue without computer. Okay, ezzel? Okay. All right. Control L. All right. That should work. All right. So, okay, so we had this bound for the norm, and when we write this in here, then it follows that you get an estimate for the distribution of the arguments in terms of the coefficients, just in terms of the coefficients. It says basically that if you want this to be small, the first and last coefficients have to be large compared to the rest. So basically this says. So just as an immediate consequence is that there are at most that many real zeros, what is here. So just this is an estimate just in terms of the coefficients. Because what you do is you just put here j to be the 1-point arc 1 and the 1-point arc minus 1. That singles out, the argument to be 0 or pi. And this is actually an estimate which is better than previous results of Bloch, Poya, Schmidt. And basically, it's a theorem of Schur and Szegő. So from, from the Erdős-Turán second discrepancy theorem, you get immediately sharp bound for real zeros of a polynomial. And also the Szegő theorem follows immediately that if the power series has radius of convergence 1, that means that the limb sup of the nth root of the nth coefficient is 1. And it's a very simple exercise that in that case this quantity has to tend to 1 through some subsequence. If this limb sup is 1, then this is really simple. So this tends to 1. And the logarithm of this is exactly what is in the Erdős-Turán discrepancy theorem. So again, if you write the zeros in that form, and then the Erdős-Turán, the second discrepancy theorem, when you plug, this quantity in, you have this bound for the distribution. That is how far the distribution of the argument is from the uniform distribution, and the log of C and K tends to 1, because C and K tends to 1. This tends to 0. So this is exactly the Szegő theorem, that through some subsequence, the distribution of the argument is uniform. So this theorem of Turán and Szegő gave, had immediate consequences. And let me formulate a general theorem along the same line. So now we look at the Jordan curve, and a point inside that curve. So we fix a point Z0. Again, J is a subarc on that Jordan curve, and J star is a neighborhood. And again, the best result belongs to Andrzejewski and Blatt. They basically show that the Erdös-Turán estimate is true in this setting with this Bn. Now, what is Bn? That is the form of the estimate is the same. So again, we count how many zeros are in this neighborhood. We compare it with the equilibrium distribution of that J. You don't need here the absolute value, sorry. So the equilibrium distribution of J compared to the number of zeros in J star. And there is an error term, and the error term is the norm of Pn on gamma on the whole curve. And you have here something you have to divide through. And if gamma is the unit circle, like in the original Erdős-Turán theorem, then the capacity is 1. This is just 1. And if we have monic polynomial leading coefficient 1, then, and Z0 is the origin, then Pn Z0 is just An, the last coefficient. So what we divide here by is exactly An time, I mean the square root of the absolute value of An times A0. So exactly, this is the matching result. So again, the rate was sharp. And that's, in some form, it's true for a family of Jordan curves. So now let me move to orthogonal polynomials. Let rho be a measure with compact support on the plane, and we form the so-called orthonormal polynomials. So these are Pn is the polynomial of degree n with leading coefficient gamma n. So gamma n will be the leading coefficient. I assume it to be positive. And this is just the orthogonality condition that, with respect to rho, this system forms an orthogonal system, orthonormal system. So the theory of orthogonal polynomials goes back to, 200-300 years, but Erdős and Turán were among the first to get results for general weights. Earlier, rather special weights were considered. And let me recall one result from 1940. It says that suppose that the measure is the support is -1, 1, and we have an absolutely continuous measure with respect to Lebesgue measure, so W is a density function. And there is this condition that W, the density is positive almost everywhere. And under these conditions, Erdős and Turán showed that the asymptotic zero distribution of the nth polynomial is the Chebyshev distribution, what we had before. And outside -1, 1, the orthogonal polynomials behave like this, that the nth root of the polynomial, absolute value of the polynomial, tends to this function. I will talk about this condition, W positive almost everywhere. So this result says that if W is positive almost everywhere on -1, 1, then this condition implies classical behavior. What I listed is true for classical polynomials like Jacobi polynomials. And it took 40 years to have a better result. Rachmaninoff proved in 1982 that actually not just the nth root of Pn, or the absolute value, tends to, has a limit. Actually, the ratio of consecutive polynomials also converges. And it was known before, we don't prove that such a ratio asymptotic is possible only if the support is connected. So if you want to say something about orthogonal polynomials on two intervals or on a general set, then no such asymptotics is possible. So you need to revert back to the nth root asymptotic that Erdős and Turán had. So what happens now, I make some simplification. I assume that the support is, of the measure has connected complement and empty interior. For example, if the measure is supported on the real line, then this is the case. Otherwise, things can go wrong. And for the leading coefficients, there is a general estimate. So the nth root of the leading coefficient, the limit is, and asymptotically, is at least 1 over the capacity of the support. So this is true for all measures. And it turns out that several things are equivalent here. There are several statements are equivalent. The first is that the asymptotic zero distribution is the equilibrium distribution of the orthogonal polynomials. The second is that the orthogonal polynomial have a so-called nth root behavior. I don't specify this function here is the exponential of the green function. For -1, that's exactly the function what Erdős and Turán had, z plus square root of z squared minus 1 absolute value. And the third is that the nth power of the, nth root of the gamma n tends to 1 over capacity. You remember that asymptotically this is at least as large as 1 over capacity. So this tends to the 1 over capacity. In some way, the leading coefficients are minimal, asymptotically. And the third is that if you look at the supremum norm of Pn on the support of any polynomial on the support, and you compare it with an LQ norm, usually the supremum norm is much larger than an integral norm. And this fourth property says that in nth root sense they are the same. The supremum norm, and all these LQ norms are the same. So supremum norm is basically the same as L2 norm. So these are equivalent, these four properties. And if any of these is true, then we call we say that rho belongs to the regular class. Now, regularity is all over in the theory of general orthogonal polynomials. Basically, it says something like the measure is not too thin on any part of its support. And basically, it says that the orthogonal polynomials behave non-pathologically. And it turns out that this regularity, which these four equivalent properties that I just described, is a very weak assumption on the measure. Implies very weak assumption. And the original Erdős-Turán theorem is now reformulated this way, that Erdős-Turán theorem is basically a criteria for regularity, that if W, that is the density, is positive almost everywhere, that's enough for regularity. And when the support is more general, not just -1, 1, then the general Erdős-Turán criterion is this, that if the measure is something times the equilibrium measure, and this something, this W, is positive with respect to the equilibrium measure almost everywhere, then that's enough for regularity. So this is, for -1, 1, this second is just the same as the first one. It's the same formulation. And there are many weaker criteria. We know by now that this Erdős-Turán criteria is pretty strong, but anyway. No necessary and sufficient condition is known in terms of the measure itself. Erdős conjectured the following. He had a different formulation, but it's equivalent. He conjectured that regularity happens. Suppose again that the measure is absolutely continuous and supported on -1, 1. But now he assumes that W is positive. So the density W is bounded. The density is bounded. So in that case, he looks at the set where the density is positive, and what he conjectured was equivalent to regularity. was the following, that if you remove any subset of small measure of some small measure from this set, then the capacity is still large, almost the same as the capacity of minus 1, 1. Even if you remove a small subset from this set, the capacity is still almost full capacity. I mean, the capacity of the set is almost full capacity, like the capacity of minus 1, 1. The sufficiency follows from some stronger regulatory criteria, but the necessity is still not known. Okay, my next topic is spacing of zeros of orthogonal polynomials. So again, now take a measure on minus 1, 1, orthogonal, take the orthogonal polynomials, and write all the zeros are on minus 1, 1. So we can write the zeros as cosine theta jn. And these theta jn are the arguments when we project the zeros on the unit circle. They are exactly those arguments. And we talk about two types of spacing. Graph spacing means that theta j minus 1 over theta j minus 1 minus theta j is about 1 over n. And fine spacing is when this is they are very close to. I mean, this difference is very close to pi over n. So graph spacing means when you project up, then the arcs that you get on the unit circle are about of size 1 over n. And fine spacing means that their length is almost pi over n. You know, there are 2 n points when you project up and down, and so 2 pi over 2n should be like pi over n. So they are almost like equal. Those arcs are equal length. And of course, classical polynomials obey fine spacing inside the interval. And Erdős and Turán had many results in the 1930s and 40s about graph spacing. By now we know basically that graph spacing is equivalent to the measure being doubling. The doubling condition is very simple, that if you enlarge the intervals twice from its center, then the measure of the enlarged interval is at most as a constant times the measure of the original interval. It's easily, a property that you can easily check. And graph spacing is basically the same. Fine spacing is much harder to get, and Erdős and Turán had in 1940 a beautiful result. It says that if you look at orthogonal polynomials with respect to a continuous and positive weight on minus 1, 1, then inside, away from the endpoints, you get fine spacing of zeros. So it's a very, very nice behavior. And this is no longer true if this, the positivity is very important here. If W can vanish, things go wrong. And this result had a connection to some recent results. A form of universality in random matrix theory can be reformulated in terms of the asymptotics for this kernel function. So these are just the orthogonal polynomials. You take the sum, and you take it at z plus some a over n and z plus b over n, and a and b are c. And so basically, you need to get some form of asymptotics in terms of a and b. And in 2009, Lubinsky proved universality under the condition that the measure is regular. This is a global condition, and locally he needed at around the point continuity and positivity of the weight. And it turns out that this universality results, this fine zero spacing under this, this implies this result under these conditions. So rho must be regular. This is a global condition, and locally the weight has to be positive and continuous. Actually, it turns out that that type of universality is equivalent to fine zero spacing. So once you have fine zero spacing, you have this universality. Because I don't tell you what, I don't know much about it, but there is some connection. So what about general support? When, again, we are still on the real line, but as the support of the measure is not minus 1, 1. It consists of several intervals or even more general set. In that case, if I is a subinterval of the support, then the equilibrium measure is absolutely continuous with respect to Lebesgue measure, and I call by omega the density of that. So omega is called the equilibrium density. So mu is just of this form. For example, for minus 1, 1, this omega, this density function is just, we have seen this already. And so in the general case, Barry Simon and me independently, we prove the following. So if you have regularity condition and positivity of this density function at a point, then around that point, the spacing of zeros is the following, that when you multiply it, the difference of consecutive zeros by n times this density function, then you get the limit 1. So it's quite remarkable that, omega s is a global thing. The equilibrium measure is a global thing. If you change the set, the equilibrium measure changes. So in some way, the zeros feel the whole support, the whole support of the measure. And not just they feel the support, they also know where they are. So the difference of consecutive zeros tell you where they are located, the zeros where they are located. And it's something like this is actually true under this condition. So that you don't need positivity and continuity of this W around the point. It's enough to assume that the log is integrable. Then this is true almost, so it's still true in some sense. And probably the strongest, the biggest problem here is the following, that is this property, or which is the same universality true, under the Erdös-Turán original condition, W positive almost everywhere. He needed, here we need something more, this is called Erdős condition. It's not clear if it should be true or what is the situation. Finally, I go to critical points of polynomials. So take a polynomial of degree n. Let Z1, Zn be the zeros, and psi j be the zeros of the derivative. These are the so-called critical points of the polynomial. Of course, there is one few or less zero for the derivative. An old theorem, which we now call Gauss-Lucas theorem from the 1980s, says that the zeros of the derivative all lie in the convex hull of the zeros of the original polynomial. And in 1948, Erdős and Niemann proved this result, that when you take the imaginary part of the zeros of the critical points and take the average of the absolute values, then that's at most as large as the same average for the original zeros. Now I give you a homework, prove that this implies the same thing for the absolute values. So the first line, the formulation was for the imaginary parts, but then you get the same thing for the absolute values. So the average of the absolute values of the critical points is at most as large as the average for the zeros. And this was extended by the Brown and Springer. If m is bigger than 1, I think they had integers, then this average, I mean something similar is true for the mth power. And the Brown and Springer conjecture, same year, that if phi is a convex function, then when you substitute the critical points into phi and take average, then this is less than the same expression for the original zeros. And this turns out to be a very strong property. It's from the theory of majorization. And this conjecture of Erdős, of the Brown and Springer, was open for more than 50 years. And there were many other conjectures relating the Z case and psi j's. And in 2003, one of the editors of the Journal of Mathematical Analysis and Application got a paper from a young postdoc from Canada who claimed a result which solved all these famous conjectures in a very simple way. So his first reaction was to return the paper, that was impossible. But fortunately, he processed. And almost simultaneously, the Transactions got a paper from another postdoc from Switzerland who had almost the same result with very similar methods. So there were two papers almost simultaneously by Malamud and Pereira. So let me tell you the result. So an n-1 by n matrix is called doubly stochastic if the entries are non-negative, each row sum equals 1, and each column sum equals n-1 over n. Usually in double stochasticity, you need the column sums and also to be 1, but here there are more columns than rows, so you need to. Anyway, the column sums are equal to each. And we look at these two vectors. So the first vector is just the the vector formed from the zeros. The second is the vector formed from the critical point. And the Malamud-Pereira theorem says that there is a doubly stochastic matrix such that the second vector is just 8 times the first vector. It's a very, very simple relation between the zeros of polynomials and zeros of the derivative, critical points. And I find it incredible that this Gauss-Lucas theorem was there for more than 150 years, and this simple relation was not found, and eventually it was found simultaneously by two people, same year, practically same time. So let me just show very quickly that this really implies the Brown-Springer conjecture. We have this, the form psi j is now this linear combination. I can't point. Anyway, so when you substitute psi j into this convex function, you use convexity, you interchange the two summations and use that the column sums are equal to n-1 over n, you get the result. So it's really a very, very basic result. And further examples are like, there are many, many consequences. You can list many consequences like that. If all the zeros lie in the upper half plane, then for the geometric mean of the imaginary parts, you have a reverse. I'm sorry, yes, okay, you have a reverse inequality. So that's the end of my talk. With this, I wanted to illustrate the impact of Erdős' work. I wanted to illustrate that even though Erdős may not have had the strongest results or the most general results, or he may not have had the tools to get those, he asked the right questions, he proved some very basic theorems that influence our work even today. So his influence is still present. Thank you very much for your attention.
Yes, thank you very much. You know the nickname for Paul is Pali in Hungarian, and when I was a beginner in English, I had the impression that the term polynomial is so named after Malamud-Pereira and Erdős. So after this thought, we are now having a break of about 5 minutes, and the next lecture starts exactly at 12 o'clock. Thank you.
The solution of that by him and co-authors. The title of the talk is on the Sanford constant is 1/3.
Okay, thank you very much. Am I audible to everybody in the room? Yes? Okay. Well, let me start by thanking the organisers for the invitation. It's a great honour, and also for assembling what I believe is the best list of speakers of any conference since I've been a mathematician. I started my PhD just after the last Erdős conference. So, I want to talk, instead of giving a survey, about quite a specific problem today, to do with sum-free sets, which is something that I know interested Paul Erdős, and also something that I personally started working on when I was a postdoc here in Budapest, so it seemed appropriate for this conference. So a sum-free set is a set of integers, although the definition makes sense in much more general contexts, like a general group. It's a set with no solutions to the equation x plus y equals z. And there's a very well-known theorem of Paul Erdős about this property from 1965, which is the one I put up there. If you take n positive integers, then you can choose 1/3 of those to be a sum-free set. And I want to give the proof of that because it's a very well-known and very, very short application of the probabilistic method, very often taught as a sort of first example of the probabilistic method. So here's the proof. For any real number theta, multiply through the elements of your set A by theta. And look at the modulo 1. And then notice that the subset of R mod Z, that's kind of the middle third, 1/3, 2/3, 1/3, the interval 1/3 up to 2/3, is sum-free. So the set that I've written there, the set of all A for which theta A lies in that middle third, is also sum-free. Essentially because theta gives you a homomorphism onto R mod Z. So the idea is just to observe that for a random value of theta, if you choose theta at random, the expected size of that set is at least 1/3 times n. So to write a few more details, if A is fixed and you choose the theta at random, then theta times A just goes uniformly around the unit circle. And so, of course, it spends 1/3 of the time in the middle third. So the probability that it lies in the middle third is precisely 1/3. And so the expected size of that set A primed theta is n over 3. And of course, the whole idea of the probabilistic method is that if you can show that the expected size of something is at least x, then there's at least one example where it's at least x. So that's it. So that was a very, very simple argument, but it's turned out to be very, very difficult indeed to improve it substantially. So as I just said, Erdős proved that if you have n integers, n positive integers, there's a sum-free subset of size n over 3. It took 25 years to improve that at all when Noguer Allon Danny Kleitman observed that you can get strictly more than n over 3, which automatically gives you n plus 1 over 3, because it has to be an integer. And Bourgain has the state of the art, which is n plus 2 over 3. It's a very, very difficult paper. And actually, a few people, I certainly have tried fairly hard to improve that, and I'm sure there are some others in the audience who might admit to it after a few drinks. Clearly, you should be able to do n plus root n over 3 or something, but somehow you can't. And actually, it's an open question whether you can get a sum-free set of size, let's say n plus 1,000 over 3 for large n. I'd like to indulge in some speculation because it gives me an opportunity to mention an open problem. Oh, another open problem. So I believe that the answer is yes. In other words, if you have n integers, n positive integers, there is a sum-free set of size n over 3 plus omega n, where omega tends to infinity with n. And to explain why I think that, I just want to say a couple of things about what Bourgain actually proved. So what Bourgain proved, as I said before, he showed that if you have a set of n integers, it has a sum-free subset of size n plus 2 over 3. But if you look carefully at his paper, he proved a slightly different bound in there. He proved that any set of n natural numbers has a sum-free subset of size n over 3 plus another quantity, which is that quantity is the L1 norm, or the integral of the absolute value of the exponential sum over a divided by log n. Now that's related to a very well-known problem of Littlewood. It's not the most well-known problem of Littlewood, but perhaps his second most well-known one from his book of problems. This quantity, the L1 norm of the Fourier transform, or the L1 norm of the exponential sum of a, turns out to be at least a constant times log n. That was known as Littlewood's conjecture. It was proven by Koniagin and by McGee-Pignot-Smith in the early 1980s. So the right-hand side here is bigger than some constant. And if only you could understand the structure of sets for which equality almost occurs in Littlewood's conjecture, then you'd surely be able to do better than this. So as I said, it's a theorem of Koniagin, McGee-Pignot-Smith that this norm of a, this weird norm of a, is at least constant times log n. You can get a constant times log n with some very, very simple sets, just an arithmetic progression of length n. Then the exponential sum is a kind of Dirichlet kernel, and it will have integral log n. I conjecture that there's at least some sort of converse to this. So in other words, if this norm of a is at most a constant times log n, well then a should be kind of like an arithmetic progression. It's not necessarily it's not necessarily close to progression. In fact, it can't even be quite a union of a few progressions. You have to allow for some multi-dimensional examples. But I drafted some notes at some point, assuming any reasonable conjecture along these lines. Assuming any reasonable conjecture along these lines, I think I can improve the sum-free set thing to n over 3 plus a function tending to infinity. So in that sense, I'm not in too much doubt as to what the answer is. Anyway, so that's all about lower bounds for the problem, and what I really want to talk about today is upper bounds. So the main theorem I want to talk about is this theorem, which is joint work with two amazing first-year graduate students of mine, Sean Eberhard and Freddie Manners, who are both here, or at least Sean's here, which shows that Erdős's probabilistic argument is basically sharp. So there exists a set of n natural numbers which does not contain a sum-free subset of size much bigger than n over 3. So specifically, not bigger than 1/3 plus epsilon times n for any epsilon. So the previous best bounds for this problem were more or less just examples of sets. So Erdős, in an unpublished letter that I saw somewhere, and then Mark Luco independently, found a set of 28 elements with no sum-free subset of size bigger than 11. So that's 11 over 28 is about 0.39. And I don't know how many people would This is not unpublished. It's published as of this morning in the book of proceedings for this volume. Nogueron showed that essentially, if you give him any example like 11 over 28, he can output a better example. And he explicitly says in the article it's 10 to the minus 50,000, but he doesn't try and optimize the 50,000 there. So what I want to talk about mainly is this theorem of Eberhard and Manners and myself. And I suppose, just to give a simple example, because if you haven't thought about this before, I mean, this would help. What's the largest sum-free subset of 1 up to n? Well, there are two examples of sum-free subsets of size n over 2. You can take the odd numbers, that's obviously sum-free, and then you can take the large numbers, the numbers between n over 2 and n. And it's a fun exercise if you get bored by the rest of my talk, or if you're already bored, to try and prove that those are the largest. So there's no sum-free subset of 1 up to n of size larger than n over 2. So that motivates this slide. If I give you a set of n integers, there are a lot of different ways in which you might try and find a large sum-free subset in there. And to prove our theorem, we're going to have to defeat all of those methods of construction. So you can, there are constructions modulo q. I talked about the odd numbers as a subset of 1 up to n. But in any set, you could just take the odd numbers in there. And unless you've constructed your set specially, that will have about half the elements of the set. So that's not going to be, we can't use sets like that in our theorem. And then there are slightly less obvious examples like mod 5. So the subset of Z mod 5 consisting of the elements 2 and 3 is sum-free. And again, unless you've somehow arranged for your set of n integers to be strangely distributed modulo 5, well, 40% of its elements will be in one of those two congruence classes. And again, that's no good for you. And then you have to defeat what I call constructions coming from the real line. You could always intersect your set X with a dyadic interval, like X up to 2X, and again, you'll get a sum-free set. So you'd better make sure that your set doesn't have a big concentration on any dyadic interval like that. So I'd call these local constructions. They are kind of different types of local constructions. Let's just look at how they look for the set 1 up to n. Well, I've said most of this already. The odd numbers have size about n over 2. The numbers congruent to 2 or 3 mod 5 have size 2n over 5. And then you could look at the numbers congruent to 3, 4, or 5 modulo 8. And again, that's slightly bigger than n over 3, 3n over 8. And then you could look at the numbers between n over 2 and n. And that is again bigger than n over 3. So I guess the point of this is that the set 1 up to n is a very, very bad example of a set with no large sum-free subset. It has a huge number of different examples of large sum-free subsets. So the aim of the game that we're trying to play is we have to come up with a set that defeats all of those local obstructions. So, well, on the previous slide, I introduced this idea of local ways of making sum-free sets. So what I've written here, this definition is designed to encode a sort of local version of the whole problem. So I'll read out the definition and then explain it. So we're taking a probability measure on Z mod QZ cross the interval 0, 1. And you want it to have the property that if you take any set inside there, in Z mod Q cross 0, 1, that's sum-free, then it can't have measure more than, just a little bit more than a third, but in this weird measure. So this won't be the uniform measure. So it's not obvious that this is the right question to ask, but you have to trust me on that one. But you can see at least that this is encoding some information about mod Q, and it's also, in terms of the interval 0, 1, something about how obstructions coming from R. So So the theorem we prove is that there are delta good measures for every delta. So you can measure subsets of Z mod Q cross 0, 1, which is somehow the space that encodes all the local information about this problem. You can find a measure on there such that every sum-free subset has measure no more than a third plus delta. And the bit that I've written there about being Lipschitz and so on is basically just saying that this measure isn't too singular. And obviously, if you go and just say that the measure of the point 1 is 1 and the measure of everything else is 0, then obviously this will work. So it turns out, and this is not obvious, that if you can solve the local problem, then you can also solve the global problem. Very roughly, the idea of how that's done is you choose a set at random according to the probability measure that you've defined. So the probability measure has been defined so that relative to that probability measure, there are no sum-free subsets of size much more than about a third. And then to recreate that in a set of integers, you use a random selection argument. So W here is the density function, essentially, of your probability. And you choose a set more or less according to that density function in the manner that I've written down there. The one extra thing is that you have to choose this number Q. So we choose Q to be some incredibly composite number, which essentially means that you've taken account of all of the local information. So Q must include all local data, mod 2, 5, 8, and so on. So the details of checking that that construction works are not at all trivial. The key ingredient is what's called an arithmetic regularity lemma, which is it's an analog for sets of integers of Semeradi's famous graph regularity lemma. And it's basically, I'll talk a little bit more about it later, but it's saying that every set of integers can be split into a structured part and a highly random part. And more or less, the structured part, all of its information is sitting modulo Q and as open subsets of 0, 1. So in that way, you can reduce the original problem to a local problem. So what I want to talk about in most of the rest of the talk is the local problem. And actually, I'm going to talk about just one special case of the local problem in which there's no Q as well. So let's get rid of the Q. So now all I want to do is construct some sort of probability measure on the interval 0, 1, such that every open sum-free subset of 0, 1 has measure less than, just a little bit more than a third. So the uniform measure will not work because the interval half up to 1 is sum-free and its uniform measure is a half, so that doesn't work. So we're going to have to construct a different type of measure that is biased against that kind of example. And actually, mentioning that example leads me on to the next point. It turns out that large sum-free sets have to be repelled away from 0. The interval 1/2 up to 1 is an example of, it's obviously as far from 0 as it could be, but it's large and sum-free. And it turns out that that's a generic phenomenon. So to combat those examples, we have to somehow define a measure that is concentrated near 0. So here's actually a formal statement of what I mean to say that large sum-free sets are repelled from 0. It turns out that the following statement is true. If you have an open sum-free subset of 0, 1, and if its measures just a little bit more than a third plus epsilon, then it actually has to avoid a definite interval about 0. So this is not obvious, and this is something I'm going to talk a little bit about the proof of, because I think some of the ingredients are sort of slightly surprising in that. I mentioned that the uniform measure is not good. It is 1/6 good. So actually understanding why that's true is perhaps just to make sure that we've got the nomenclature right. That's basically saying that open sum-free subsets of 0, 1 cannot have measure more than a half. So the main technical difficulty in our work is proving this repulsion from zero phenomenon, actually. So showing that large sum-free sets have to avoid a neighborhood about zero. And what I want to talk about first is how you would go from that to constructing these good measures. So if you know that a sum-free set is repelled from zero, how do you construct a measure that's concentrated enough near zero that it works for what we want? And the idea is to do an iterative process. So we have the uniform measure is already 1/6 good. It turns out that one can iterate and get better and better and better measures by repeatedly using this repulsion from zero phenomenon. So I should warn you that the next slide, well, it's not super technical, but it has some actual mathematics on it. So bear with me a little bit. So here's the idea. So suppose you've got a measure that's delta good. So with respect to that measure, sum-free sets have measure at most a third plus delta. I claim that the measure I've written there, I'll say what the symbols mean in a moment, is delta primed good for some slightly better value of delta primed. So this is pi star just means the pullback of the measure nu under this map pi, and pi is contracting the whole interval 0, 1 into this little forbidden interval that I had on the previous slide in the proposition about repulsion from zero. So I know that large sum-free sets are repelled from zero, so I'm going to define a measure that sort of deliberately weights that interval that they're repelled from. So I claim that that measure is better than the measure I started with. And if you think a little bit about the iteration that I've set up there, its fixed point is epsilon. So all you have to do is you start with the uniform measure, which is 1/6 good, and just apply this a load of times, and eventually you'll get as close to epsilon as you like. So you can get very, very good measures this way. And actually, I mean, the way I've written it down here is maybe a little bit abstract looking, but you could write these down very explicitly. And they're sort of extremely heavily concentrated towards zero, but still continuous. So the remaining half of this slide is just explaining this claim. Well, just reminding you what that means. I've got to show that a sum-free set with this new measure does not have measure more than a third plus delta primed. So there are two cases. That sum-free set could have uniform measure more than a third plus epsilon. But if that's the case, then we know that it repels from zero. So it completely misses that little interval about zero. And because of the way I've set things up, well, one of the two terms in the definition of nu is then completely zero. So I've defined this measure nu so that it very heavily concentrates things towards the disallowed interval, 0 epsilon primed. And then, of course, the contribution from the remaining bit, 1/4 mu is just a probability measure, so that's less than 1/4, less than or equal to 1/4, and certainly less than a third. So that's kind of the trivial case. And the second case is when that's not true, so the uniform measure of S is pretty close to a third. But then we can use the fact that the pullback of S under this contraction is still sum-free. And so if you measure it with respect to the measure that we input to this algorithm, it measures at most a third plus delta. And then if you do the computation, the new prime measure of S comes out to be what I said it is, so less than a third plus delta prime. So this is actually very similar to the proof of the contraption mapping theorem, actually, for those of you who studied that. I think that was the inspiration for it. So to recap what happened there, if you know that large sum-free sets are repelled away from zero, you can construct a measure that's so concentrated near zero that all sum-free subsets with respect to that measure have density not much more than a third. So it all comes down then to proving this fact about repulsion from zero. So if you want, you can completely forget about the previous slide. This is what we have to prove. So if you have an open, sum-free set, and its measure is a little bit more than a third, then it avoids some interval about zero. So why is that true? Well, it turns out that it has something to do with sets with doubling constant less than 4. So why is that? Well, if you're sum-free, then these two statements are true. S minus S is the set of all pairwise differences of elements of S, and that has got to be disjoint from S. If it's not, then you have a solution to x minus y equals z, which gives you a solution to x equals z plus y. And similarly, S minus S must avoid minus this SS. So these are all very easy observations. And just to remind you, that's what I mean by S minus S. So all of the sets I've written down there, S minus S, S, and minus S, those all sit inside minus 1 up to 1. So there's not that much room for S minus S, and that forces it to be small. So its measure is at most 2, obviously, because it sits inside minus 1 up to 1. But it also has to avoid S and minus S, and those are disjoint sets. So its measure is actually at most 2 minus the measure of S, minus twice the measure of S. But if I'm assuming that the measure of S is bigger than a third, well, that means the measure of S minus S is less than 4/3. And so its doubling constant is less than 4. So it's an example of a set which, when you subtract it from itself, I mean, usually doubling constant is thought of in terms of adding a set to itself, but subtraction is quite similar. When you subtract it from itself, it expands by a factor of less than 4. So just to get a bit of intuition for that, well, what are some examples of sets that expand by less than 4? You could take an arithmetic progression that expands by a factor of about 2. Or you could take a dense subset of an arithmetic progression, provided it's pretty dense, it will still expand by a factor of not much more than 2. But as soon as you take any two-dimensional, sort of like a box in R2 or Z2, then it will expand by a factor of 4. So this doubling less than 4, one feels, is imposing a kind of one-dimensionality on the set. And that's a crucial intuition for studying those kind of sets. So for those who, I mean, this hypothesis is very related to the hypothesis of Feynman's theorem. So Feynman's theorem is about the structure of sets with doubling less than, let's say, 10 or 100. But Feynman also had some theorems about sets with doubling 2 or 3, and proving much stronger structural statements there. And what we're after here is more in the spirit of those than in the spirit of his bigger theorem. So I pointed out in the short calculation I did there that if you have a sum-free set of measure more than a third, then it has doubling less than 4. And so why don't we try and prove about a structured theorem about sets with doubling less than 4? So the statement at the top, which is what I really needed, about sum-free sets being repelled from 0, is a consequence of the statement at the bottom, which says that if you have a set of doubling less than 4, then S minus S contains an interval about 0. So if that's true, and if S is sum-free, then because S minus S is disjoint from S, then you get the statement at the top. Okay, so have a look at the theorem at the bottom there. That in turn is implied by the following slight variant of it. So I claim that under the same hypothesis that the doubling of S is less than 4, then S has density strictly bigger than a half on an interval of length epsilon primed. So the way you go from that to the statement I had before, well, if you have density bigger than a half on an interval, I think this is an observation due to Lebesgue or something, then that set, the different set of that set, contains a whole interval. It's actually a very easy argument to show that. So this is the theorem that I'm really after now.
Can you repeat
Yeah, if you have a subset of an interval of 51.51 density, then A minus A will contain a little interval of length 0.01 or something like that. I think it would be familiar to... There is a result in sort of measure theory about measurable sets containing A minus A containing an interval, and it's the same argument. So this is the fact that we're after. So it's a little bit of a Freiman-type theorem. So it says if you have a set with a doubling less than 4, then it has some structure that's a bit related to an arithmetic progression. Specifically, on an interval, it has density strictly bigger than a half. And I've somehow reduced everything to that statement. So here's where things get a bit hairy. To study sets with doubling less than 4, we use this arithmetic regularity lemma a second time. So as I said before, this is a structure theorem. Well, it's usually a structure theorem for sets of integers, but by sort of various limiting arguments, you can use it to get structure for open subsets of an interval as well. So there are many different levels on which to understand this. Very roughly speaking, it says every set up to negligible errors, and negligible always depends on what purpose you want it for. Up to negligible errors, your set is structured. And you have to understand what you mean by structured. And here, well, it's not going to look the prettiest when I write it, but there's a picture on the next slide, I promise, that should elucidate things. So our notion of a structured set is I'm going to call it, for now, a set of Bohr type. And what you do is you take a homomorphism from the real line to a finite dimensional torus, and you make sure it's sort of a highly mixing sort of homomorphism. So you map to this torus by some highly independent elements x1 up to xd. So when you do this, over any short interval, this homomorphism will equidistribute very, very rapidly over the whole torus. That's the point. And then you pull back a nice subset of the torus. So you take a nice open set, sigma I, in the torus, and you pull it back under this homomorphism. But you don't do that globally. You first divide into subintervals. And then you might take a different set on each one. So this turns out to be the appropriate notion of structured. So a structured set, you divide 0, 1 into finitely many parts, boundedly many parts, and on each of them, your set is the pullback of a nice open subset of the torus under an extremely nicely mixing homomorphism. And here is a ridiculously rough statement of the arithmetic regularity lemma. Basically says that an arbitrary open set, if you're prepared to ignore some negligible errors, set of measure epsilon, is extremely well approximated by sets that look like this, sets of Bohr type, with all of the parameters, the dimension of the torus, the number of intervals you had to divide in, and somehow how complicated the sets in the torus are. Those are all bounded. And here, well approximated, well, it means fine for our purposes, but again, it depends what you need it for. So there'll be a picture very shortly. The purpose of this text here is just to remind you what we're trying to do. So again, the aim is to show that if you have an open subset of the unit interval, if its doubling is less than 4, then it has density strictly bigger than a half on an interval. So applying that regularity lemma, and fudging quite a lot, you can assume that the set is actually of this particular structured type. Now, that's a hand-drawn version of it. Does that come out? It looks okay. So this is my attempt to draw what a set of Bohr type might look like. So there you can see I've subdivided the interval 0, 1 into 2 bits. And I've written my rapidly mixing homomorphism, pi, in there. And that's a two-dimensional torus. And you can see that I've pulled back 2 different sets on that torus, and they're both sort of fairly low complexity open subsets of the torus. I've got sigma naught on the left and sigma 1 on the right. And then I've given a very schematic depiction of what it might look like downstairs. So that's somehow how you should think, maybe, of these sets of Bohr type. The crucial thing I want to get across is that the density of this structured set on an interval is the same as the measure of the set in the torus. So on the left, I don't know what the measure of sigma naught is supposed to be, maybe a third. It looks like about a third to me. And hopefully downstairs, I've colored in 1/3 of the interval 0 up to a half. And then on the right, the measure of sigma 1 is maybe, I don't know, 1/8 or something. And I've colored in 1/8 of the points. So the reason I mentioned that is that if any of those sigma i's occupy more than half of the torus, then you're done. Because what we want is precisely that S has density more than a half on an interval. So we can assume that not only is our set of Bohr type, so it looks like you've pulled back these open subsets of tori, but furthermore, all of those open sets have measure less than a half. And somehow the point is that if you have subsets of the torus of measure less than a half, they've got to grow quite a lot. I mean, if you take the whole torus, then it doesn't grow at all under taking the difference set. I mean, the difference set of the whole torus is just the whole torus again. But if you take an open set of measure less than a half, and you take its difference set, then it really has to expand a lot. And here's a formal statement of that principle. I was delighted to find that this was published in one of the world's higher quality journals in 1953 by McBeath. So if you take open subsets of a torus in any dimension, and if they both have measure less than a half, then when you take their difference set, well, the size of the difference set is at least the sum of the sizes of the sets. So you get, in particular, if you get one set of density less than a half, then it expands under taking the difference by a factor of at least 2. So you can sort of see, looking back at the previous page, that we've got this picture where somehow we have tori above 0, 1. And we now know that we're going to get a factor of expansion that's at least 2 from all of the tori, from all of the sets in the tori. And also, actually, the interval itself expands by a factor of 2. If you take 0, 1, form its difference set, that's minus 1 up to 1. So we can expect to win a factor of 2 in the tori and a factor of 2 downstairs, and that makes a factor of 4 in total, and then we'll get a contradiction. So the actual way that we get a contradiction is, well, let me go back to the previous slide. We've got these sets that sit inside tori above the interval. But if we now just replace them by intervals, just delete the tori and replace each torus by a copy of the real line, and replace each of those sets sigma I by just an interval of size, of height sigma I, or the volume of sigma I. So that will now be a subset of R2. And because of this McBeath theorem, when I had subsets of the tori, they expanded at least as much as this new set that I've drawn. So this is known as a compression argument. Actually, its first place, I think the first time I saw it used for some sets was in a paper by Baylor and Imre Lieder. So I've made a set S tilde, and it's now an open subset of R2. It's got no tori involved. It has the same measure as S. It's a different, I'm now using Lebesgue measure on R2, but it's the same measure. And because of McBeath's theorem, the amount it grows under differencing is at most the amount that S grows under differencing. So when you add sets like this, the amount of expansion is no more than the amount of expansion you had in the torus. And it turns out that if you now apply the Brun-Minkowski theorem, that immediately tells you that any open set of R2, in fact, has doubling at least 4. So here's a statement of the Brun-Minkowski theorem that states that if you take open sets, in fact any sets in Rd, then the measure of x plus y to the power 1 over d is at least the measure of x to the power 1 over d plus the measure of y to the power 1 over d. And if you apply this here, with x is s tilde and y is minus s tilde, you get that, that this set s tilde has doubling at least 4. But as I said, s tilde was made, it was designed to have doubling smaller than the set S that I actually cared about, which had all these tori, yet I'd assumed that that set has doubling at most 4 minus epsilon, so that's a contradiction. Okay, that was all a bit hardcore at the end, and I think it would be fitting to end Paul Erdős style with quite a large selection of open problems. How long do I have time to cover all of these? Okay, so a few slides of open questions. So the first one is, I suppose, an obvious one. You might ask, we showed that if you have a set of n positive integers, there is a set of n positive integers with no sum-free subset of density more than a third plus epsilon. How about you try and find a reasonable dependence of n on epsilon? And it will be of little surprise to a lot of people here that because we used a regularity lemma, in fact we used it twice, we get just appalling bounds. So certainly one of those applications of the regularity lemma can be removed, but the other one can't be yet. So at the moment epsilon would be something like 1 over log star n, or possibly even worse. And for all I know, it could be 2 over n. That's Bourgain's lower bound. Here's another problem. How about, there are actually it's reasonably easy to write down some examples of sets that ought to work. I have to say, I haven't thought about this very, very hard, but I don't think I know of any sum-free subsets of this set, if J is large, with density much more than a third. So somehow this set has been designed, it's sort of an arithmetic progression of length n dilated by some very rapidly growing sequence of factorials. And it's been deliberately designed to defeat all of the constructions I mentioned earlier, mod, q, and certainly it doesn't intersect x up to 2x in any set of reasonable size. A little bit related to that, here's a problem that came up in our work, which I'm quite fond of. If you have an open subset of 0, 1, of measure more than a third, does it have a solution to x, y equals z? I doubt most people remember the definition of a good set, but somehow, if you take logs, you end up back at something like the original problem. So this would let you construct very explicitly and in a very natural way a delta good measure. But I think the problem's sort of interest in its own right. So now looking a bit further afield. As I said, I've been talking about sum-free subsets of integers. But the definition makes sense in any abelian group, and if you replace sum by product in any group. So if G is a group, what is the largest product-free subset of G? In the alternating group, there's an example that was mentioned to me by somebody I was an undergraduate with called Edward Crane, which is very nice. If you take the following set of permutations in the alternating group, so the set of all permutations that map 1 into 2 up to m, and then everything between 2 and m outside of that range, so into m plus 1 up to n. It's pretty obviously product-free, because if you look at what happens to 1, well, if you just, under pi, it gets mapped into 2 up to m, but under the product of two elements of this set, it gets mapped first into 2 up to m, and then outside of that set. So it's obviously product-free. And then, of course, m is a parameter you're free to choose, and if I did the calculation correctly, it's optimal when m is square root n over 2. And then the size of A is what I wrote down there. And the question is this optimal for large values of n? So is that the largest product-free subset of the alternating group? Since Tim Gower's work on quasi-randomness in groups, where he actually was the first person to solve, it's not obvious. There could be positive density product-free subsets of the alternating group, but Tim actually showed that there are none of density larger than about n to the minus 1/3, so he falls just short of this bound, but he certainly proves that they have zero density. But nonetheless, it's natural to use Gower's arguments, which use some representation theory on this group. And David Ellis and Max Menzies and I spent some portion of some summer thinking about that and got a little bit of the way. I mean, it's clear that you have to understand the first non-trivial representation, and once you've done that, that's about it. So the permutation representation. And here's a slightly fun thing. Kiran Kedlaya, I'm not sure this is the paper of which he's most proud, but still, proved in 1997 that that every group has a product-free subset of size at least mod g to the 11 over 14. I haven't looked at that paper recently, but from memory, it uses the classification theorem. So basically, you observe that if you have product-free subsets lift well under homomorphisms, so the hardest case is simple groups, and then you just go through the simple groups, because I've got this unspecified constant little c, it suffices to work with the families. And then I think he does something like look at their lowest dimensional representations and pull back a neighborhood of minus the identity or something like that. The question is, can the constant 11 over 14 be improved? I don't know. Again, now that Gower's work is available, that may be more tractable. So to finish, I want to mention one further open problem, which is not quite sum-free, but is somehow much more mysterious. This is a question of Erdős and Moser from 1965. So it's about a very small tweak in the definition of sum-free, which is that of a sum-avoiding set. So the problem is almost exactly the same. You have a set of n integers, and you want to pick out a set A primed in there with no solutions to x plus y equals z, but now only x and y have to be in A primed, and z could be in A. So this gives the problem a completely different flavor, and it's actually very, very open. So Sudakov, Semerady, and Vu show that there is always such a set of size at least log n times a function that tends to infinity. I actually don't know. It was earlier shown that it's at least a constant log n. Maybe Erdős did that. Certainly Ruja had a better constant there. Well, where would you get a 5-fold iterated logarithm? Well, it's actually because they use Tim Gower's bounds on Semerady's theorem inside that. So I had a French master's student, Jahan Douce, last year, who was able to improve that, not by improving Tim Gower's bounds on Semerady's theorem, but by what you actually need, it turns out, is kind of like a progression of progressions of progressions, but of length 3. And that turns out you can get better bounds for that. So that, I believe, is the state of the art. And probably if you went far enough into Bourgain's techniques, you could probably remove another log there. And then, well, the upper bound is a beautiful construction of Ruja, which shows that it's not a polynomial in n. So there do exist sets of size n with no sum-avoiding subset of size e to the constant root log n. But there's clearly a very big gap between these two. And that's the end. Thank you.
Thank you very much for the interesting talk. Are there any questions? No questions. Thank you once more. Don't leave yet. There is an announcement to be made.
Before the lunch break, I would like to give you a couple of announcements or give away important things which you might keep in mind. Most of this information is included in the information sheet you got in your conference package, but my experience is that giving away written information is, the value of that is close to nothing. People just don't read them. So first of all, it's really nice to see so many of you here in Budapest, and we are pleased with this crowd being interested in the conference. However, it makes certain difficulties for us. The building is just not designed for 700 people, so it's a little bit I mean, we need your cleverness to move around the building. So if you found any part of the building a little bit congested during the coffee break, or if you are looking for a restroom, just please try to use the map which is given in the middle of the program, program booklet. Try to locate another facilities, and there should be somewhere else a place where you can have easily a coffee or something similar to that. Another important question is please, or request is please do wear your badges all the time. 700 people around certainly raises certain kind of security measures, so we need to be sure that all of those who are in the building, they really are trustworthy participants of the conference, and many of the people in the building don't know you personally, so the only way they will recognize you, that you have a right to be here, that you wear your badges. The same will apply on the boat, on the banquet cruise on Thursday afternoon. Everybody is supposed to get a cruise ticket, which you are supposed to pick up, or you were supposed to pick up from the registration desk. The staff of the registration reported me that there is a big discrepancy, more than 100 people between the number of registered participants and those who picked up their tickets. So if you have not picked up your boat ticket and you plan to attend the boat cruising and the banquet on Thursday afternoon or Thursday evening, please, during this lunch break, go down and pick up your boat ticket. Almost surely you will be allowed to enter the boat only with your ticket. Please do that. An information which I hope is going to be completely useless, but it's better to know about that. We have an emergency room in the building. It's just on this floor. At the other end of the corridor, there is a physician on duty and also a staff of an emergency car. I hope we will not need to use it, but the healthier you are, the better you know where it is, because probably the others will need your help in case of emergency. You have to guide somebody to that. So please note that on the map of the building there is an emergency room. Note it and try to locate it. The secretary of the conference is just behind me over there. Of course, you have to go around the corridor. You can find any kind of assistance over there, especially from tomorrow on. Also, we have a handful of workstations, 6 or 7 workstations, in case you don't have your laptop or the Wi-Fi is very congested, then you might try to go there and use those computers. They also have a limited capacity of printing and copying. Next to the secretariat, also in that part, we have a book exhibition. We have here Cambridge University Press, Oxford University Press, American Mathematical Society, Springer and Elsevier. They are all exhibiting their books. Also, the Bolyai Society is going to display and will sell from tomorrow on the Bolyai Society Mathematical Studies volumes, including the volume Ben just referred to a couple of minutes ago, the volume of the recent conference. Also, we will have on display this one. Also, the first tale book about Paul Erdős will be displayed, and you can probably order that, I think, from tomorrow on. Two more announcements. One about lunch. Probably everybody is interested in lunch. So in your conference, on the website of the conference, there is a link to the nearby restaurants listed with comments about what type of food and what prices you can get that. Based on a request, we also made plenty of printed copies of those pages. Either you find it in your conference package, or if you picked it up yesterday earlier, then probably it is not there, then you can find plenty of those copies down before you leave the building at the registration area. Also, within this building, there is a lunch served in the Academic Club restaurant. This is the venue where we had yesterday evening the reception. It has a limited capacity of about 250 to 300 people per day. The menu, the lunch menu of that restaurant is in your conference baggage. You might not, I'm not sure how it will work out. I'm not sure how many people will go there, but please keep in mind if it's congested, probably you want to find another place in the neighborhood. And last but not least, an announcement which you usually hear in a theater, but I think it's just proper to pay our thanks to the distinguished speakers by please switching off or at least switching silent your mobile phones. It's just proper, I believe. Thank you very much.
Oké, jó, csak Fali